Welcome to the deep dive. Today, we are pulling back the curtain on a world we can't see, but one that really shapes so much around us, the world of radioactivity.
It's everywhere, even if we don't realize it.
Exactly. We've been digging into the fundamental physics behind matter and radiation, and our mission today is to unpack the core concepts of radioactivity for you. We want to figure out, what it actually is.
Right, the basics.
What forms its energy and particles take, how this invisible process actually happens inside atoms.
The mechanics of it?
Yeah, and where it pops up in our lives, and importantly, both its powerful uses and the significant risks it presents.
It's definitely a double-edged sword.
It's a deep subject, no doubt, but let's dive in and hopefully find some surprising insights together.
Sounds good. So where do we start? At its most basic, radioactivity is really about instability. It's happening inside certain atomic nuclei.
The core of the atom.
Exactly. Picture that nucleus, protons, and neutrons bundled together. Sometimes that arrangement just isn't stable. It's got too much energy or the wrong proton-neutron mix.
Okay.
So when these unstable nuclei spontaneously break down or transform, they release energy and particles. That whole process, that's radioactive decay.
And it can actually change the element itself.
Often, yes. That's called transmutation. The nucleus changes its identity.
Okay, so this unstable core is giving off stuff. But it's not just one kind of emission, is it?
No, not at all. There are three main types we usually talk about: alpha, beta, and gamma radiation. You can think of them as different ways these stressed out nuclei shed that excess energy or mass.
Right. Let's take them one by one. Alpha first. What is an alpha particle? What's actually coming out?
Okay, alpha particles are, well, they're pretty chunky, relatively speaking. They're essentially the nucleus of a helium atom.
So 2 protons, 2 neutrons.
Exactly, all bound together. And because of those 2 protons, each alpha particle has a positive charge, specifically plus 2e. They're quite heavy compared to the other types.
Okay, heavy particles. So what does that mean for how far they travel? Can they go through things?
That weight, that bulkiness, it makes a huge difference to penetration. Alpha particles have very, very low penetrating power.
Right.
They bump into air molecules, atoms, and materials very easily. They can be stopped completely by just a few centimeters of air. Or, get this, even a single sheet of paper.
Just paper. Yep.
Yep. A standard sheet of paper is enough shielding for alpha radiation externally. But, and this is a big but, despite being stopped so easily on the outside, if you were to ingest or inhale something emitting alpha particles,
Oh, okay.
they become incredibly dangerous inside the body. Because they're heavy and charged, they dump all their energy very quickly, causing intense ionization, stripping electrons off atoms in a very short path. That does massive damage to living tissue locally.
So can't get through skin,
Yeah.
but devastating if it gets inside. Or if the source is right on your skin.
Yes, it can cause nasty skin burns if the source is in direct contact. And because they're charged, they also get deflected by electric and magnetic fields. They bend in the opposite direction to negatively charged particles.
Fascinating. That contrast between easily blocked and potentially harmful is quite something. Okay, moving on then. What about beta particles? How are they different?
Beta particles are way, way less massive than alpha. They're essentially high-energy electrons or their antimatter counterparts, positrons, that get ejected from the nucleus.
Electrons from the nucleus. How does that work?
Well, it's a transformation. In one common type, beta minus decay, a neutron inside the nucleus actually changes into a proton. To make everything balance, it emits a high-speed electron that's your beta minus particle with a negative charge, E.
Ah, so the neutron becomes proton and spits out an electron.
Basically, yes. There's also beta plus decay, where a proton becomes a neutron and emits a positron, which is like a positive electron plus E. But the key thing is they're fast light particles.
And how does that affect their penetration? Can they get through paper?
Oh yeah, they go right through paper. Much higher penetrating power than alpha.
Yep.
To stop beta particles effectively, you typically need something like a thin sheet of metal. Maybe aluminum, less than a millimeter thick, often does the job.
So a bit more shielding needed.
A bit more, yes. They still ionize gases and materials as they pass through, including tissue, but it's generally less intense ionization over a longer path compared to alpha.
And fields. Do they bend in fields too?
They do. Being charged particles, they're also deflected by electric and magnetic fields. Beta minus particles bend the opposite way to alpha particles because of the opposite charge.
Okay, so paper for alpha, thin aluminum for beta, because a clearer picture. What's the third one? Gamma rays. They sound different. not quite particles.
You're right, they are different. Gamma rays aren't particles with mass in the same way. They are electromagnetic waves like light or X-rays, but with extremely high energy.
Wow.
Very short wavelengths, very high frequencies. They're basically packets of pure energy photons traveling at the speed of light. And crucially, they have no electric charge and practically no mass.
No charge, no mass. So how do they even interact with stuff? How far can they go?
Well, that lack of charge and mass is exactly why they are so penetrating. They don't interact nearly as readily with matter as alpha or beta.
Makes sense.
So gamma rays can sail straight through things like cardboard, aluminum, even thin layers of denser materials. To really stop or significantly reduce gamma radiation, you need substantial shielding. Think thick lead or lots of concrete.
So they just keep going.
Pretty much, until they have a direct hit with an atomic nucleus or electron. While they cause less ionization per interaction compared to alpha or beta, their sheer penetrating power means they can travel deep into materials, including our bodies, depositing energy and causing damage over a wider area.
Okay, let's recap the shielding then. Paper stops alpha. Thin aluminum stops beta. But for gamma, you need thick lead or concrete. That's a huge range.
It really highlights how fundamentally different these three types of radiation are.
Definitely. Okay, we've got a handle on what comes out, but let's go back inside the nucleus. How does this decay actually happen? And how do we even talk about how fast or slow it occurs?
Right. This gets into the idea of radioactive isotopes, or radionuclides. Remember, atoms of the same element always have the same number of protons that defines the element.
Yeah, the atomic number.
Exactly. But they can have different numbers of neutrons. These different versions of the same element are called isotopes. Now, many isotopes are perfectly stable, but others have an unstable mix, maybe too many neutrons, too few, or just too much energy packed in there. These are the radioactive ones.
The ones that decay.
The ones that will spontaneously decay to try and reach a more stable state.
And you mentioned this involves the nucleus actually transforming. Can you walk us through that for each type?
Sure. For alpha emission, like we said, the nucleus kicks out an alpha particle, 2 protons, 2 neutrons. So the original nucleus loses those. Its proton count, Z, drops by 2. Its total count, A, protons plus neutrons, drops by 4.
And it becomes a different element.
It has to. Change the number of protons, you change the element, that's transmutation.
Yeah.
A classic example is radium-226, element 88, decaying by alpha emission to become radon-222, element 86, different element entirely.
Okay. What about beta decay? You said a neutron changes.
In beta-minus decay, yes. This often happens when a nucleus has too many neutrons for stability. One of those neutrons effectively transforms into a proton. To conserve charge and other things, it simultaneously emits an electron, the beta particle, and another tiny particle called an antineutrino.
So the key change inside is?
The nucleus gains a proton. Its Z increases by 1, but since it lost a neutron and gained a proton, the total number of nucleons, A, stays the same. Again, element change. Carbon-14, 6 protons, 8 neutrons, does this, becoming nitrogen-14, 7 protons, 7 neutrons.
Wow. And beta plus?
Similar idea, but kind of the reverse. A proton changes into a neutron, emitting a positron, a positive electron, and a neutrino. Here, the nucleus loses a proton, so Z decreases by 1, while A still stays the same. Less common in nature, but important in some medical imaging, for example.
And gamma, does that change the element?
Gamma emission usually doesn't change the nucleus's proton or neutron count directly. It's more about energy. Often, after an alpha or beta decay, the resulting nucleus isn't quite settled. It's in an excited, higher energy state.
Like it's still vibrating or something?
Kind of, yeah. To calm down, it releases that excess energy as a high-energy photon, a gamma ray. So Z and A stay the same during the gamma emission itself, but the nucleus drops to a lower, more stable energy level. You often see gamma rays accompanying alpha or beta decays.
It's amazing to think of these fundamental particles just switching identities inside the nucleus. You mentioned earlier that individual decays are random, though. We can't predict when one specific atom will decay. So how can we possibly measure or predict anything about a whole sample?
That's where statistics comes in, and it's incredibly powerful here. It's called the radioactive disintegration law.
Yeah.
While any single decay is totally unpredictable, a chance event.
Right.
For a large number of identical radioactive nuclei, the rate at which the whole group decays is perfectly predictable. It turns out the number of decays happening per second is directly proportional to the number of radioactive nuclei you still have left at that moment.
So the more you have, the faster they decay overall.
Yep. Exactly. And the relationship involves a specific constant for each isotope called the decay constant. But the concept that's usually easier to grasp is half-life.
Ah, yes, half-life. I've definitely heard of that. What does it tell us?
Half-life, often written as TIRO, is beautifully simple. It's the time it takes for exactly half of the radioactive nuclei in your starting sample to decay.
Half of them. Okay.
So let's say you start with, I don't know, 1 billion atoms of a particular radioactive isotope. After one half-life period, you'll have about 500 million left.
And after another half-life?
You'll have half of that left. So about 250 million, then 125 million after the next half-life, and so on. It keeps halving. And the crucial thing is, for any given isotope, its half-life is a constant. It doesn't matter if it's hot, cold, under pressure, in a chemical compound, that half-life is fixed. It's purely a property of the nucleus.
Like an internal clock.
Precisely, an unchanging nuclear clock. For example, carbon-14, which we'll talk more about, has a half-life of about 5,730 years.
Wow. Okay, so half-life tracks the amount dwindling over time. Is there a term for the decay rate itself? Like how many decays are happening right now?
Yes, that's called the activity, usually symbolized by A. It's literally the rate of decay, the number of disintegrations happening per unit time, usually per second.
And there are units for that?
The standard international unit is the becquerel, symbol BQ. 1 becquerel means 1 disintegration per second. It's named after Henri Becquerel, who discovered radioactivity.
1 per second sounds small.
It is quite small for practical amounts of material. You often deal with kilobecquerels, KBQ, or megabecquerels, MBQ. There's also an older unit, the Curie CI, which is still sometimes encountered. 1 Curie is a huge amount of activity, about 37 billion becquerels. It was originally based on the activity of 1 gram of radium-226.
Okay, becquerels for activity. And that activity decreases over time too, right? Following the half-life.
Exactly. As the number of radioactive nuclei decreases by half each half-life, the activity, the rate of decays per second, also decreases by half.
Got it. So we've gotten from unstable atoms spitting out particles through nuclear changes to these concepts of half-life and activity that let us track it. This is some deep physics, but how does this connect to the world around us? How do we actually use this stuff?
Oh, in so many ways. One of the most famous applications directly using that fixed half-life idea is radioactive dating, especially carbon-14 dating.
The one used for old bones and stuff.
Exactly. Because carbon-14 has that reliable 5,730-year half-life, it acts like that atomic clock we mentioned, allowing scientists to estimate the age of organic materials, things that were once living, like wood, charcoal, bones, shells, plant fibers, anything up to maybe 50,000 years old or so.
How does that clock actually work? How does the C14 get in there and then tell us the time?
It's really quite elegant. See, carbon-14 is constantly being made up in the Earth's atmosphere when cosmic rays hit nitrogen atoms. This radioactive C14 mixes with regular, stable carbon-12 and gets incorporated into carbon dioxide.
Which plants breathe in?
Right. Plants take it in through photosynthesis, animals eat the plants or eat other animals that ate plants. So while an organism is alive, it's constantly exchanging carbon with its environment, and it maintains about the same ratio of C14 to C12 as exists in the atmosphere at that time.
Okay, a steady level while alive.
But the moment that organism dies, it stops taking in new carbon. The stable carbon-12 just sits there, but the radioactive carbon-14, it starts to decay and it's not being replenished.
So the C14 amount starts dropping.
Exactly, dropping predictably with that 5,730-year half-life. So if archaeologists find, say, an ancient wooden tool, they can measure the ratio of C14 to C12 remaining in the wood. By comparing that ratio to the original atmospheric ratio, they can figure out how much C14 has decayed, which tells them how many half-lives have passed since the tree it came from died.
And that gives the age. That's
Yeah.
genuinely amazing. Using atomic decay to date history.
It revolutionized archaeology, paleontology, climate science. Really incredible.
Are there other big uses mentioned beyond dating?
Oh, lots. Radioactivity is used all over the place in medicine, industry, research. For instance, cobalt-60, it emits powerful gamma rays. It's used to sterilize medical instruments, surgical gloves, even food sometimes to kill bacteria and prolong shelf life.
Right, I've heard of food irradiation.
And it's also a key tool in cancer treatment radiotherapy, using those gamma rays to target and destroy tumor cells.
Okay, what else?
Let's see. Sodium-24 is mentioned. It emits beta and gamma rays and has a short half-life, making it useful as a tracer. You can inject a tiny amount into a pipeline, for example, and then use detectors on the surface to find leaks underground.
Clever.
Uranium-235, of course, is the primary fuel for most nuclear power plants, generating electricity through controlled nuclear fission.
Big one.
Then there's plutonium-238. It's an alpha emitter with a decent half-life, around 88 years. It generates heat as it decays, and this heat can be converted into electricity. It's been used as a long-lasting power source for spacecraft, especially deep space probes like Voyager, Pioneer, Cassini, New Horizons, things going far from the sun where solar panels aren't practical. Some have been running since the 70s.
Powering spacecraft for decades, wow. Any others?
Americium-241, another alpha emitter. You actually find tiny amounts of it in most household smoke detectors. The alpha particles ionize the air in a small chamber, allowing a current to flow. Smoke particles disrupt that current, triggering the alarm.
No way, it's in smoke detectors.
Yep. And it's also used in some security scanners at airports to help detect explosives hidden in luggage, again, using its specific radiation properties. So yeah, the applications are incredibly diverse.
Incredibly useful then. But obviously there's the other side. Radiation can be harmful. How do we measure that potential harm to living things? It can't just be about the energy, right? You said alpha was different.
Exactly. We need different units. First, there's the absorbed dose. That measures the raw energy deposited by radiation per kilogram of tissue. The unit is the gray. G-way. 1 gray is 1 joule of energy per kilogram.
Okay, energy absorbed.
But, as you said, different types of radiation cause different amounts of biological damage even if they deposit the same amount of energy. Alpha particles, dumping their energy densely, are much more damaging biologically than gamma rays, which spread their energy out more.
So we need to account for that difference.
We do, and that's where the effective dose comes in, measured in sieverts. SOV. To get the dose in sieverts, you take the absorbed dose in grays and multiply it by a quality factor, or radiation weighting factor, sometimes called Q factor or RBE.
And that factor is different for alpha, beta, gamma.
Yes, for beta particles, gamma rays, and X-rays, the weighting factor is 1, so 1 gray equals 1 sievert. But for alpha particles, because they are so much more damaging biologically over their short range, the weighting factor is 20. 20. So 1 gray of absorbed dose from alpha particles is considered to deliver an effective dose of 20 sieverts. It's considered 20 times more biologically harmful than the same energy dose from gamma rays. That's why internal contamination with alpha emitters is such a serious concern.
That Q factor really highlights the difference. Okay, so sieverts measure the biological risk. Where are we actually encountering radiation in our daily lives? Is it all man-made?
Not at all. We're constantly bathed in low levels of natural background radiation. It's unavoidable. A huge chunk of it, maybe around half the average dose for many people, comes from radon gas.
Radon.
Yeah, it's a radioactive gas produced by the decay of uranium naturally present in rocks and soil. It can seep into buildings from the ground and build up, especially in basements or poorly ventilated areas. Since it's a gas, you can inhale it, and its decay products, which are alpha emitters, can irradiate lung tissue.
Okay, that's significant. What else?
Cosmic rays, high-energy particles from outer space, constantly bombard the Earth's atmosphere, creating secondary radiation that reaches us. We also get doses from naturally radioactive elements in the food we eat, the water we drink, and even in our own bodies, like potassium-40. And of course, radiation from the soil and building materials around us.
So it's just part of the planet.
It is. On top of that natural background, the biggest human-made source for most people is medical procedures, X-rays, CT scans, nuclear medicine treatments. Then there are much smaller contributions from things like nuclear power under normal operation, past weapons testing, fallout, certain consumer products, etc.
And high doses are definitely bad.
Absolutely. Ionizing radiation damages living cells. It can ionize water molecules, creating harmful free radicals. It can directly damage DNA, leading to mutations. These mutations can sometimes cause cells to become cancerous, potentially years later.
So cancer risk.
Yes. It can also cause other effects like cataracts, damage to the blood-forming tissues, weakening of the immune system, and genetic effects that could potentially be passed down. Very high doses delivered quickly can cause acute radiation sickness and can be fatal.
Which really underlines why safety is so critical when working with radioactive materials deliberately. What are the key rules?
The fundamental principles are often summarized as time, distance, and shielding. Minimize the time you spend near a radioactive source. Maximize your distance from it. Radiation intensity drops off rapidly with distance, usually following an inverse square law.
Double the distance, quarter the intensity sort of thing.
Exactly. And use appropriate shielding between you and the source. As we discussed, what constitutes appropriate shielding depends heavily on the type and energy of the radiation. Paper for alpha, thin metal for beta, thick lead, or concrete for gamma.
Makes sense.
Beyond that, never handle sources directly with bare hands. Always use forceps, tongs, or remote handling tools. Store sources securely in properly shielded containers when not in use. Maintain good hygiene, no eating, drinking, or smoking in areas where radioactive materials are handled to prevent accidental ingestion. And ensure there are strict protocols for the safe disposal of radioactive waste.
Clear, crucial steps. Okay, one last practical thing.
Yeah.
If this stuff is mostly invisible, tasteless, odorless, how do we actually detect it? How do safety officers know if there's a problem?
That's where radiation detectors come in. A very common type, the one people often associate with that clicking sound, is the Geiger-Müller tube or GM tube.
The Geiger counter.
Right. The heart of the Geiger counter is often a GM tube. It's basically a sealed tube, usually cylindrical, filled with a specific type of gas at low pressure. There's a central wire electrode running down the middle, held at a high positive voltage relative to the tube's outer wall. When a particle of ionizing radiation, alpha, beta, or even a high-energy gamma-ray photon enters the tube, it collides with gas atoms and knocks electrons off them, creating ion pairs.
Ionizing the gas.
Exactly. Now, because of the high voltage, the freed electron is rapidly accelerated towards the central positive wire. As it zips through the gas, it gains enough energy to knock more electrons off other gas atoms it hits.
A chain reaction.
Kind of, yeah. It's called a Townsend avalanche. Those secondary electrons also accelerate and cause more ionization. You get this cascade, this avalanche of electrons hitting the central wire all at once from just one initial ionizing event.
And that creates a signal.
It creates a detectable pulse of electrical current. The electronics connected to the tube register this pulse. Each pulse corresponds to one radiation particle being detected. These pulses can be counted electronically to measure the radiation rate, or often they're amplified and sent to a speaker to produce those audible clicks. Each click means radiation has been detected.
So that's the click. One particle detected. Simple, but effective.
Very effective for detecting the presence of radiation and getting a rough idea of its intensity, though basic GM counters don't usually distinguish between radiation types or measure energy precisely. Other types of detectors exist for those purposes, but the Geiger counter is iconic for a reason.
Okay, so we've really covered a lot of ground. From these unstable atoms spontaneously breaking down, emitting different kinds of radiation with vastly different properties.
Alpha, beta, gamma.
Through the way nuclei actually transform, the predictability of decay rates using half-life and activity.
That amazing nuclear clock concept.
To the incredible range of uses, from dating ancient history and powering spacecraft to treating cancer and finding leaks.
Sterilizing things, detecting smoke.
Right. While also acknowledging the very real dangers and the absolute necessity of understanding dose, using shielding, and following strict safety procedures.
It truly underscores the immense power locked away inside the atom, doesn't it? Studying radioactivity reveals these fundamental processes that shape our world, from the age of the Earth itself to cutting-edge medical tech. It's a force that demands understanding and respect.
It really does. And maybe a final thought for you, our listener, to ponder.
Yeah.
We talked about how the decay of any single nucleus is fundamentally random, unpredictable. Yet when you have a large enough sample, the overall decay follows that incredibly precise, predictable half-life. How does that stark contrast between complete randomness at the individual level and near perfect predictability at the collective level, how does that make you think about chance and order and predictability in the universe? Something to chew on.